All right, everybody, let's get started. Welcome back. Today is our last lecture on centroids. Just to remind everybody on the schedule, we will be celebrating on Friday, November 15th, so 2 weeks from today, okay? We are going to have, so this is our last centroid lecture, so that means we have next week and then the following week, so that means we have 4 lectures on our next topic, which is structural analysis, and then we have an exam review on that Wednesday and an exam that Friday. Then what we're going to do the following week, 2 lectures on friction. I'm going to give you Friday off because it's Thanksgiving, and then that is not only is that homework that week, the last homework before break, it is the last homework of the class. Because we will come back after Thanksgiving break and review Engineering 213, comprehensive review. That's what we're doing when we come back. Sound good? Okay. So today what we're going to do is close out our discussion on centroids, and there is a slight inaccuracy in that statement because we've already stopped talking about centroids. What we're going to be doing is discussing the moment of inertia. And we already talked about that from a calculus-based perspective, but what I want to talk about is how you actually do it practically. And you can't do it practically without an expression or a utilization of the parallel axis theorem. Okay? So I want to explain what that is today and how it works. So just a little background. We've talked about the area and then moments of area. So if we wanted to calculate area, we would integrate dA. If we wanted to calculate the 7th moment of area, it would be the integral of x to the 7th times dA. In engineering, the first and the second moments of area are the only ones that are really useful. The first moment of area is critical to locating the centroid, and then the second moment of area is called the moment of inertia. Okay? We talked a little bit about how they have a profound impact on structural response, and we talked about like the idea that like here's my little surface pen, and you can kind of see it's got like a rectangular cross section. It's stiffer this way than if I were to bend it this way. Like imagine if any of you have a ruler in your hand, right? It's flimsy one way, it's really wavy and flimsy, but if you were to take it 90 degrees and try and bend it about the sharp side, I guess you would, it would be very rigid. It's very hard to do that. And that's because it has a higher moment of inertia about this axis. Now what we typically are interested in a moment of inertia calculation is a moment of inertia. So if we have a given cross section, okay, what we're interested in is a moment of inertia that references a particular coordinate system. So we want the moment of inertia about this origin. And where do you think that point is? The centroid, okay? That's what we're interested in, okay? So the idea is, okay, so let's deal with a really, really simple shape. Let's say I had a rectangle, okay? And I wanted to find the moment of inertia about, let's say, the x-axis. So this is the x-axis, this is the y-axis. If I wanted to find the moment of inertia about the x-axis. So the moment of inertia about the x-axis would be the integral of y squared dA. Okay? So let's talk about that. Okay? So first off, what would dA be? Well, dA would just be a little sliver of the rectangle this way. So dA would now just be b dy. And what would our limits of integration be? We would go from the bottom of the rectangle to the top. So y equals negative h over 2 to y equals positive h over 2. And if you look at this integral, this should be something that you should be able to do by hand, right? I mean, if y is the variable and everything else isn't, what you can do is just carry it through, like factor the b out, okay? And so what's the integral of y squared? Well, the integral of y squared is going to be y cubed over 3. Plug in the top number, minus, plug in the bottom number. You see where I'm going with this, right? So the moment of inertia of a rectangle, specifically, so what I'm calling the moment of inertia about the x-axis, but I'm calling it IXC because I'm saying it's the x-axis where the centroid is. that moment of inertia is computed as BH cubed over 12. So maybe over here on this board I should put some C's here so you can kind of see what I'm talking about. So C, 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 C. Most of the references that you use will probably leave that off, but you can kind of see what I'm talking about here. Okay, so if I wanted to compute the moment of inertia of a rectangle, the moment of inertia of a rectangle would just be BH cubed over 12. It's one of those formulas that you'll just kind of remember throughout your engineering curricula, so I would just sort of keep it in the back of your head. But that's how we would do that for a simple rectangle. Does that make sense? Okay, now what I'm interested in, by the way, is not how to compute the moment of inertia of a rectangle. I'm interested in how to compute the moment of inertia of something like this, right? Something that is much more arbitrary and much more complicated. And the point I'm making is, if I wanted to compute the centroid of something like this, how would I do it? I would break it up into simple shapes, right? To determine properties of each one of those shapes, and then there's an algorithm, right? I propose that the same thing is true for the moment of inertia, okay? So we're going to do the same thing. So I have here the moment of inertia of a rectangle. If you open up your textbook will list moments of inertia of various simple shapes. And I've put some of those here on the board because I noticed that the textbook is either really heavy or really digital, and you may or may not have it with you, so I figured let's just go ahead and have it here for reference. But every one of these are within your textbook that you can very easily find. One of the things I'll mention is you might want to pay attention to the notation. So, for example, let's take a look at the triangle. The triangle is kind of easy. So the triangle actually does do this. So look here, I've got a triangle that's B wide and H tall, okay? Now, it lists two moments of inertia. It lists an IX and then this sort of IX bar, this IX prime. That's sort of the one that we're going to use because that's referencing the centroid. The other one references the bottom. Okay, which does have applications, but for the purposes of what we're doing here, we're just interested in the centroidal moments of inertia for what we're going to do. So like for the rectangle, just use the one with the bar, or the one with the bar, so on and so forth. Okay, make sense? And just so everybody is aware, we are not going to use it, but if you're wondering what they are, so we have the moment of inertia about the x-axis, which is the integral of y squared dA. We have the moment of inertia about the y-axis, which is the integral of x squared dA, something like this. So what if you have the integral of xy dA? I think the textbook calls that J. It's a polar moment of inertia or a mixed product of inertia. So if you see these J terms, I think that some textbooks refer to that differently, but I think that's what that's calling it here. Sometimes they just call it IXY, sometimes they call it J, but we're not using those. So, okay. So far, so good? Okay. Now, like I said, so the analogy with centroids is, so what we did with a centroid is we took a complex shape, broke it up into simple shapes, determined properties for each one of those shapes, plugged it into an algorithm, right? So the way a moment of inertia is going to work is the same idea. We're going to break it up into simple shapes, determine properties of each of those individual shapes, and then plug it into an algorithm, okay? The name of that algorithm is going to be the parallel axis theorem, okay? And I want to take some time and explain how this works, okay? Like I said, we are interested in locating moments of inertia with respect to the centroid, okay? So let me sort of give you the motivation maybe here on the screen. I'll do the motivation here on the screen, okay? So let's come up with a simple shape. Let's take a plate with a hole in it, okay? Where is the centroid of that hole? I don't know, like right there? Okay, where is the centroid of the whole plate? The plate with the hole in it? I don't know, maybe like right there? Does that sound about right? So here's the thing. In order to add up moments of inertia, what we need to do is reference them with respect to a common coordinate system. So when I look up the moment of inertia of a circle, bless you, when I look up the moment of inertia of a circle and it tells me that the formula is pi r to the 4th over 4, it's referencing that with respect to the center of the circle. What I need to be able to do is reference that to the centroid of the whole shape, okay? Now the trick that we use is this, okay? Here's the trick that we use. So if I have the moment of inertia as the integral of, let's say, y squared dA, okay? If I want to reference this with respect to a common axis, what I'm going to do is I'm going to take this and I'm going to shift it, okay? And the way I'm going to shift it is I'm going to say y plus some shift, okay? And then the shift is going to be however far the distance is from here to here. That's going to be my little shift that I do, okay? All right, so how does this work? Okay, so here's going to be my moment of inertia, and here's going to be my new moment of inertia. I'm going to shift it, okay? All right, let's break out the algebra, okay? What do I do with this? How do I expand this? Break out a little bit of that aluminum foil, right? And so we do front, outside, inside, last, right? So then I got a bunch of terms. I'm going to take those terms, do what I can do with integrals. The integral of the sum is the sum of the integrals, right? Factor out my constants, maybe turn it into something about like that, right? Okay, so I got 3 different integrals, okay? So I have the integral of y squared dA, right? That's my original moment of inertia, right? Okay? I've got this one over here. So this integral over here is the integral of dA, which is just the area times d squared. So this is what I'll call AD squared, right? And then I've got this. This references the centroid. But the whole point of this exercise was and to determine the moment of inertia with respect to there, right? Technical terms, I know. So what are the coordinates of the centroid if I place the axis right here? 0, 0, right? So what I'm saying is this whole integral goes to 0, right? Does that make sense? So that goes to 0, and now I'm left with this thing right here. That if I have a moment of inertia and I want to reference it with respect to a new axis, I can take that moment of inertia and add AD squared. Area times the distance between the parallel axes squared. Get it? Parallel axis theorem, right? So the algorithm for the moment of inertia is this, okay? If I want to find the moment of inertia of a composite shape, what I do is I take the moment of inertia of each individual shape and I add AD squared. Area of each shape, and then D. You would think that the tricky part is how to compute D, but that's actually really easy because all I do is I take the distance for each individual shape minus the centroid for the whole thing. Okay, this is actually the easiest part. It seems challenging, but it's really easy. And one of the other things kind of interesting is, does it really matter which direction I do the subtraction? Like, could I do y bar minus yi? Does it really matter? Why does it not matter? Because I'm squaring it, right? Whether I do this minus this or this minus this, I'm getting a number and then I'm squaring that number. It's going to come out positive, right? It's not going to matter. Okay? So now I have an algorithm for computing the moment of inertia for an arbitrary shape by splitting it up into a series of simple shapes. Okay? So in order to exercise that, let's look at the following problem. Okay? So I'll show you how this works. And by the way, this is another one of those methods that's very Excel friendly. Okay? So we're going to compute the moment of inertia with respect to the centroidal x-axis of the following shape. So here's sort of, if you want a physical understanding of what we're doing here. Okay? So, oh God, please forgive my horrible 3D art skills. So let's say I had a beam that was made of this, that was extruded in 3 dimensions. And let's say that I decided to stand on top of this beam. What we are computing is a moment of inertia that would express how stiff it is this way, right? So the moment of inertia about the centroidal x-axis would tell me how stiff it is this way. So if I wanted, what I could do is I could repeat, after we do this problem, I could literally repeat the entire exercise by taking this and turning it 90 degrees and doing it again. And it would tell me which is the stronger direction. And by the way, which do you think is the stronger direction? This way or turning it? The first way? See, I would argue the other way because I think it's longer this way. Like think about this. Like if you have a backyard patio, right? Right? Here's you, right? Here's the table with the umbrella and the grill and the propane tank, whatever, right? The floor beams are like this, right? This is how the floor beams are oriented, right? They're long way up, right? I think that this is probably, like if I were to turn it, I think it's longer, it's stiffer that way. Maybe I'm wrong, but does that kind of make sense? Like think about a ruler, right? The ruler is flimsier this way than it is this way. I'm saying that that in this direction, it's sort of like standing on it on the flimsy side, and if we were turning on it, it's probably more the stiff side. That makes sense? Of course, the only way to actually figure that out is just do the math and see, like to actually quantify it. Okay. All right. So here's what I'm going to do. I'm going to split this up into what I think is a pretty easy to figure out series of simple shapes. Okay? So okay. And what we'll do is we'll say, let's number them. So we'll call the rectangle, we'll deal with the rectangle first. We'll deal with the triangle second. We'll deal with the semicircle third. And the circular hole fourth. And by the way, each one of these shapes is going to have positive contributions except the last one because it's a hole. Does that make sense? Everybody, so far so good? Now, okay, the goal is to compute the moment of inertia with respect to the shape's centroid, right? But in order to do that, we first need to figure out where the centroid is. Like, we don't even know where the centroid is for this location. So we are going to need to pick a reference coordinate system right off the bat. So what I'm going to do is this. I'm going to say that's my reference coordinate system. So that when I start computing things, I'll have something to go off of. Okay. All right. Yes.
Do we have enough information here to do this? We don't have the overall height or like the radius of that semicircle or diameter.
Well, did I not give the? Did I not copy? What's that?
You gave the diameter.
Oh yeah. Let's talk about that actually. So yeah, this is 4, right? So, I'm glad you brought that up. That was actually my next note. Did you get a sneak look at this before? Yeah, you're right. This dimension doesn't look like it was explicitly given, right? But let's look at the semicircle. If the radius of the semicircle is 4, what is the diameter of the semicircle? 8. And so that makes this height 8 inches. Remember in Engineering 102 when I said only place a minimum number of dimensions necessary because the more you place, it all comes full circle. All right. Okay. All right. So let's, you go away. All right. Okay. Let's start computing some properties, okay? Let's start off with the rectangle. Okay, for the rectangle, the first thing, so we're going to need, for this algorithm, for this computation of the moment of inertia, we're going to need 3 properties, okay? And let me do some notation here. So let me do A sub 1, okay? So we're going to need 3 properties. The first thing we're going to need is the area of the rectangle. What is the area of the rectangle? 80, right? Because it's 10 times 8, which is 80 square inches. Okay? The next thing that we're going to need, so if we're computing a moment of inertia with respect to the centroidal x-axis, we're going to need y distances. So let's do a y1. Okay? So y1 is going to be how far is it from the origin to the center, the centroid of that rectangle vertically. So how far is that? Is it 3 or is it 4? Because the rectangle is 8 inches tall, right? So we're talking about just the rectangle. To get to the center of the rectangle, we're going 4 up, right? Right? Okay. Now, we are also going to need a moment of inertia. We're going to need a moment of inertia with respect to the x-axis. Now, we derived that for a rectangle, right? We derived that, and I have that listed up here. That is BH cubed over 12, where B is the horizontal distance and H is the vertical. Okay? So this is going to be, this is our first time dealing with these formulas. And so in these formulas, the order really matters. B is the horizontal, H is the vertical. The order really matters. Okay? And so, what are we getting for this? We'll say 2 decimal places. Do I have a second? Because everybody brought their Casio FX115 ES Plus or similar scientific calculator on a Friday at 11 o'clock. I know they did. Now, the units are inches to the 4th. That I know. I'll just level with you. That seems like a really weird unit to wrap your head around, like length to the 4th, because you think like length, area, volume. What? Like what's a 4th dimension? You know, it's not. That's not really what it is. It's a second moment of area. It's an area times a distance, but we're taking that distance and squaring it. So that's why the units come out like that. Yes. Okay. There we go. All right. Okay. Is everybody good with that? Everybody okay with this? Okay, so let's look at this triangle. Okay, so with the triangle, we're saying the width and the height. Okay, so let's see if we can figure a couple things out. So first off, what is the area of the triangle going to be? I mean, what is the area of a triangle? 1/2 base times height. 8 over 2 is 4. 4 times 8 is 32. Okay. Y sub 2. Ooh, I didn't give you that one. Let's see if we can remember this. How far from the bottom, the green coordinate system, to the centroid of a triangle? Everybody's saying, I can see it, h over 3, right? We go a third up, right, for a triangle. So 8 over 3, that's going to be like 2.67. Right. A little more than 2, a little less than 3. Okay, now the moment of inertia. Now, like I said, I went ahead and gave you this. Again, you can look this up in your textbook. I went ahead and gave you this. It's BH cubed over 36. Again, the order really matters. Oh, wait, I got a typo there. Okay? So 8 times 8 cubed, so 8 to the 4th over 36. 113.78. Do I have a second? Okay. Okay. How are we doing so far, so good? Okay. Now for the semicircle and the circle, this is actually pretty serendipitous that the moment of inertia about the x-axis and the y-axis is actually the same. So it doesn't matter. So for the semicircle, it's pi r to the 4th over 8, and for the circle, it's pi r to the 4th over 4. So that part's going to be pretty easy. So that we don't have to do so much scrolling. Let's see if we can just at least write down our y distances really quick. What's the y distance for the semicircle going to be? How far is it from the horizontal x-axis to the centroid of the semicircle? We'll call that y3. Say it again. 4. It's 4. It's not that 4r over 3 pi business that we were using, because that's the centroid this way. The centroid up and down, I mean, how far is it from the bottom to the middle of that? It's just halfway up. Okay? And for the circle, how far is it from the centroid of the circle to the horizontal axis? So we're talking about, what we're talking about is how far is it from here to there? That's y4. 5 inches, right? This is 5 inches. Okay, does that make sense? And then y3, what we're talking about is if the centroid is about there, we're talking about that. All right. Does that sound good? Okay. So now that I've written that down, okay. So let's do 3 and 4. So 3 is, so that's the semicircle. And what I'll say for that is the radius is 4. So that means the area is pi r squared. Oh, no, it's not.
Is it 1/2 pi?
1/2 pi r squared. So what do we got? We got 4 squared, 16 over 2, 8. So 8 pi. So pi is 3.14. So it's about 24, 25 or something like that.
25.13.
There we go. All right. Y in this case is going to be 4 inches. And IX3, again, pi r to the fourth over 8 over 8. Okay. So 16 times 16 over 8. So let's see, that's 16 pi. Or wait, no, I don't know. 100.53?
Yep.
32 pi, that's what it is. I need to improve my mental math skills. I'm going to be being a math field day coach here soon, so I got to, you know, got to get ready for that. Okay. All right, so, anybody do math field day? Okay, all right, we got a few people. Okay, all right. Remember when they had just like the yarn on the one to like estimate how long it is? That's
Give you a jar and just
how many jelly beans are in it? Yeah. Okay, what was the radius of the circular hole? 1.5. Okay, so the area. So here's what I'm going to do. I'm going to say pi r squared.
Shouldn't it be negative?
Yeah. So it's pi. So here's what I'm going to do. So let's just do this, and so when we do that, we're going to get 7.07. Because here's the point. You'll see what I'm doing. So I'm going to put a little sign there to say it's negative. But here's the. You're right. Okay, you're right. It's negative. But there's a reason I'm doing it like this. Okay. Oh. So y sub 4 is 5 inches, and then ix sub 4 is pi r to the fourth, in this case over 4. Okay, and what does this come out to be? 3.98.
Shouldn't the moment of inertia on shape 3 be inches to the fourth?
Oh, you're right. Whoopsie. Okay. Now I wrote it like this. I love my sound effects. All right. All right. I love my job. All right. I wrote it like this because I wanted to ask a question. This is negative. We all agree that it's negative because it's a negative area. Is this negative? No, that's a coordinate. Okay? That's a coordinate. Okay? Now, I want to ask your intuition. Is this negative? What's your intuition? Is this negative?
yes.
Why? So the people that are saying yes, why is it yes?
Because if it was there, it would, like the way it's turning, would the mass not being there makes it go the opposite way.
Okay. Why?
It's going to shift where it is on the whole shape, the total moment of inertia.
So you're saying yes or no?
Yes or no to what?
Is this positive or negative? Like, what's that?
Negative.
Negative. Okay. The folks, has anybody said positive? Why did you say positive?
Well, wouldn't it be shifting
So, okay.
on the axis?
All right, this is good. All right, so here's the answer. I want to tell you why. The answer is it's negative. Okay? Now let me tell you why. Because the questions about shifting, I don't think that's the right interpretation. This is the algorithm that we're going to be using. So we're going to be summing these. Okay? So what we're doing is we're summing up all of the components that contribute to the stiffness of this element, okay? This is a whole, right? It does not contribute stiffness. It, in fact, removes stiffness. So not only is the area negative, but this is too. Now this isn't negative, that's just where it is. Okay? Does that make sense? Okay, so I wanted to, I did it that way because I wanted to have that discussion as to whether or not what values were what. Okay. Does that make sense? Everybody okay with that? So that's why the I is negative and the A is negative, but not the Y. And now the Y could be negative if the hole was down here, you know, below the x-axis, but it's a different question. Okay? Sound good? Okay. Now, I'm going to go ahead and prepare you. We're going to do a parallel axis theorem calculation, and we're going to have a big table. Okay, it's going to have 7 columns. So just be ready for that. Okay. Now, in order to compute the moment of inertia, we're going to need 2 formulas. First thing we're going to need is that, because we are going to locate the centroid. We're going to need that. The second thing that we're going to need is what I'm going to call this. Oh, sorry. Okay. And I'm going to go ahead and write this down because I threw that there on the slide. And I just wanted to have that there for reference. Okay. 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 So, how many shapes do we have? 4? Okay. Okay. The first 3 columns past this is going to be very familiar because we're going to be locating the centroid just as we have this whole time. Okay? So we're going to have an area column in square inches. We're going to have this column in that. And we're going to have that right here. Nothing here should be really that different, okay? So now what I'm going to do is I'm going to list the properties that we've already computed. So, you know, if you scroll up, we'd already done, you know, A1, A2, A3, A4, Y1, Y2, Y3, Y4. So I'm just going to list the properties that we've already computed. So this is 80, 32, 25.13, and negative 7.07. Drop that down a little bit. And then we had done the Y's. We got that this was 4, this was 2.67, this was 4, and this was 5. And notice how we're being cognizant of our signs, right? All the Y values were positive because they were all going from the bottom of the shape measured up, right? All the areas are positive except the area for the circle. That's negative. It's not contributing stiffness. So now what we're going to do is 80 times 4. And if it's okay, I'm going to do this part with for you. 320. This is 85.33. This is 100.53. Negative 35.34. Okay? Is it okay that I'm going this fast on this? We've done this before, right? Okay? So what would I do then to locate the centroid? I would sum this column, and then take the quotient, right? Divide those two, and I would get y bar. So let's go ahead and do that. This is 130, so let's put a sum right here. This is 130.06. And this is 470.52. So just, right down here, I'm going to say y bar is 470.52 inches to the third over 130.06 inches squared. And then when you divide that out, you get 3.618. Is everybody okay with that? Okay. All right. Okay. All right. So the next thing that the next column that I'm gonna declare is, I'm gonna call this IX0 or IX0. And I'm calling it IX0 because I'm gonna say these are the moments of inertia of each shape. But these moments of inertia are referenced with respect to their individual centroids, not the centroid of the whole thing, okay? So I'm going to list the values as we computed them, because we got 426.67, we got 113.78, 100.53, and negative 3.98. That's what we had computed. Okay. So far, so good? Okay. Now, I want to explain what we're about to do with this D column. So let me do my best here. Because this is a whole lot easier than a lot of students make it out to be. So let's do this. Okay. Let's take the triangle. Help me out with the triangle. Where is the centroid of the triangle? It's about right there. What is the y bar? 2.67? What is 2.67? Where is it measured from? The bottom, right? Is everybody okay with that? How far, okay, now that's my first question. Here's my second question. How far do I need to go up from the very bottom to the centroid of the whole thing? 3.618, right? So if I were to draw, oh, the hole, forgot the hole. If I were to draw this line right here, that's y bar 3.618, right? Okay. If that's the case, how far is that? What's this distance? It's the difference between the two, right? See, what we need to do is shift these. We need to shift each one of these values, and we need to shift them from here to here. So we need that D shift distance, okay? Now, it doesn't really matter what order you do it in, right? You could do it as, like I think I wrote it backwards here on the slide. But it really doesn't matter what order you do it in, because why doesn't it matter? Because what we're going to do is square it, right? So what I'm going to say here is that this is 3.618 minus 4, 3.618 minus this, 3.618 minus this, 3.618 minus that, right? So this is going to be negative 0.38. Yeah, so I guess I'll be consistent and do that. Doesn't really matter, but it's okay. Let's see, this is positive 0.95. I'm just going to 2 decimal places. Negative 0.38 and negative 1.38. see what I'm doing? So, like, for example, if we picked, I don't know, the last one. This is going to be 3.618 minus 5, minus that one. Okay? Make sense? So we just do that for each one, and then now all we have to do is compute that. Okay? So how does that work? So we're going to take I plus AD squared, right? So what we'll do for the first computation here, I'll erase this. So we'll take that plus that times that squared. I'm curious what everybody's getting for that. I want somebody to do that one just to make sure we're comfortable with this. So I plus AD squared. And I did it with Excel, so my numbers might be a little different than yours. I'll write mine down. You may get a little bit different than rounding. That's okay. 438 point something. All right. I got 438.86. But it's not going to matter because we're going to round somewhat liberally at the end. 438.86. Is that okay? Again, I'm tracking decimals like all the way through because I did this in Excel, so mine might be a little bit different than yours. That's okay. Everybody okay with that? So this is 142.72, 104.21. This is negative 17.48. Is everybody okay with this? So if I sum this column up, I'm going to get 667.8. So if you want an answer, we get that. I'm curious, can a moment of inertia be negative? Ever? No, it can't. Everybody's like, maybe, stop. I imagine many of you don't get that reference. Look it up. A game show called Pressure Luck. All right. Okay. Now listen. A moment of inertia is a reflection of stiffness. So any area, any shape with some defined area is going to have a moment of inertia. Let me ask it this way. Could you have a shape with a negative area? I mean, you could have a hole, but like just a shape by itself. Like you can't, it doesn't make sense, you know? Like this hole could be negative, but not for the whole shape. Okay, is that everybody good? I'm gonna pull up the code one more time, and that's all I got. I will see you all on Monday.